wonderful world of traffic statistics, it falls upon me to bore you to death with numbers. So yeah, counting for beginners. It sounds simple in principle, but it's a little more tricky than you might expect. Does this work? Yes. So my original plan was to actually rant about the things like flow statistics, because that's really getting under my skin. So we have S-flow and IP-fix, where you have to, it's easy to think, okay, I start counting at the beginning of the frame, which is a destination MAC, and then I just count. But what do you count? Do you include the tags? Do you include the checksum? Do you include padding? So I had a whole thing prepared for that, because different vendors do different things. The difference between S-flow and IP-fix, and then I had to scrap it because there was something else that we needed to look at, and that was the big elephant in the S&P room. For those of you who have actually checked our traffic statistics lately, you might have noticed a not so small gap between input and output. So input is actually what you're sending to us, and output is what we're sending to you. So that's the perspective that we have to this. And in principle, an IXP is a closed system. What comes in has to go out, and we shouldn't make up traffic ourselves. And it looks like here we're making up a lot of traffic ourselves. So first thought you have with something like this is we're sending broadcast, unicast, multicast. It must be something like that. We're amplifying something. But if you actually look at the packet rate, we see that it's level. Input-output packet rate is almost the same. So yeah, what do you then do? There's no evidence for this. This is actually a graph I made then of looking at the difference between bits per second input-output and packets per second input-output. And you see that for packets, that's the green line, it's almost 0% difference. So we're doing something, but what are we doing? And yeah, so the first question that you then have to ask is, well, when did this start? And you take the yearly graph of traffic that we have, and then you zoom in and you try to eyeball it, and you say, well, that's roughly, let's say, September last year. That's when it started. And then you actually take a look at the numbers, and you analyze it a bit further, and then you see, again, if you look at traffic in-out difference and percentages, there was an interesting jump here somewhere in June 2023. And if you followed Leroy's presentation, then you know that was the first big migration that we did. And that was when the gap started to appear. The second gap that really, where it jumped up, was the NICF, an interaction migration. And from then on, as we kind of kept migrating, the gap just became bigger. So for some reason, this must be related to the Juniper migration. And in fact, last year, I already noticed a little bit of discrepancy. And at first I thought, well, it might be because maybe Juniper counts the packet size slightly different than Extreme, and we have a mixed environment. So if the Juniper, for example, we know that Juniper doesn't count the frame checksum as part of the frame. So maybe it counts 4 bytes less per packet. And if the output is more on the Extreme side and the input is more on the Juniper side, you could get a discrepancy. But what I would expect is that over time, this kind of flattens out. There's more, as you migrate more and more to Juniper, the gap grows a bit, but at some point it just goes to 0 again because everything is Juniper. It turns out that that's not true. And if you look at the numbers right now, so pretty much everything is Juniper. If you calculate average packet size, then you see that there's just about a 1% difference in sort of average packet size that you would expect. And that's stable. So yeah, where does it come from? We started, it's nothing serious, so it's not really an operational issue. Nothing is broken. But at some point you start asking around, and we did a team session, and where's Gary? Gary, raise your hand. Yes, so Gary was my partner in crime here. I started asking questions like, what could it be? You know, what's a possible reason for this gap? So the first thing is it our S&P polling? Turns out, no, not really. You can actually check what the counters are from the command line on these boxes, and then you check it with what you actually poll from a remote client. There's no difference. So, next one. Typical one is, do we miss ports in our total count? Because of course, to add up all the total traffic, you have to add up all the customer ports and not put in any backbone ports. Did an analysis on that. Nope, that's not a problem either. Also, because if we would miss ports, you would typically see a difference between input and output packets. And again, we see no difference there. So, could it be a field that is somehow counted by the Juniper on egress, but it doesn't count it on ingress? I don't know. At some point, you start grasping at straws, and you know, wild theories fly over the team session. It's not something that you do 24 hours, right? It's every day. You think for about an hour. Let's try this theory. So it's like sort of a break you take to start hypothesizing. So again, go back to the original diagram. So what could be possible sources of bytes that might not be counted in one direction, but maybe in the other? Yeah, it's a difficult question to answer. So let's check. Is it the CRC, the frame checksum? So that was the first one that we looked at. Well, we know that Juniper boxes don't consider it as part of the frame, so maybe they somehow count it on ingress and not on egress, or the other way around. It's 4 bytes. That's actually not even enough to explain the difference. If you multiply 4 bytes by the number of packets that come in, it's not even enough to fill the gap of input-output octets. So that one was also not supported by lab tests. So that's a no. Okay, next one. Always a good one is the Q-tag header. So Q-tag, what if all the input traffic is untagged and all the output traffic is tagged? Right? Then in principle, you add a Q-tag to every outgoing packet, which would influence the outgoing octet count. 4 bytes. Again, not enough. Still not enough. So, is it? Yes. Still not supported by existing data. That's a no. So then, you know, you really start to go into hallucination territory, and you think, is it frame padding? Right? Because frame padding is somewhere in the range of 0 to 42 bytes. You might get away with it, you know, it could be. But that would mean that for some reason the device discards frame padding on ingress for the octet counters and then adds it frames. It's not happening. What else? What do we have? I couldn't sleep anymore. So fortunately, again, Gary does the tests, and we found out some bursty behavior in S&P octet counters, and related to a very specific line card. So we have 2 line cards currently in the platform, which is the LC2101 and the LC9600. And if you actually start putting a stream of traffic between a port on the LC9600 and another port on the LC2101, and every 30 seconds you kind of compare the counters, you see that for a number of 30-second periods, the output that's on the LC2101 is always lagging the input by about 1%, and then every couple of polls, it actually spikes up. So it tries to catch up, and then the ratio gets reversed. This only happens to the octet counter, so the packet counters are still perfectly equal. So, then what do we do? We've only tested this on a device in the lab environment. So what does it do in the production environment? Could it be that this is affecting RRD algorithms? Because when we take the data from SNMP, we store it in RRD files, and RRD has this way to take out spikes. So if it says, if you have a port that's 90% loaded, and then suddenly there's a little spike, it might go over 100% of the port capacity, and in that case, RRD says, well, I'm going to flatten that spike. So that's something that we're seeing. And indeed, how does it behave in production? So, question, is it an RRD artifact? The thing is that if it has to be an RRD artifact, you really have to have a pretty large set of consistently highly loaded ports, like over 90%, and it has to be throughout the day for it to have any effect. And we just don't have that. We don't have enough ports that are so highly loaded throughout the day, and the few ports that we have simply cannot support this. So then let's look at the raw data. Like really, just I do polls. I tell the software to do polls every 5 minutes from the platform, and just take all the raw SNMP counters that we have, dump them in a file, take them from 5 minutes apart. Then select the customer ports only. Then calculate the throughput over the interval. It's all pretty basic, and then add it all up. But this is without any flattening, any curving on it. It's just looking at the raw data. You add it all up, and there we have it. It's exactly just about 1% difference between output and input, again, and the packets are perfectly balanced. So we have a winner. We now know, to my great relief, that it's not the polling software, it's not in the storing of statistics, it really is, it's the counters. So now what? We know that there's something funny about how the SNMP octet counters work, especially on the LC2101 line cards. We do have a case open with Juniper right now to look into the bursty behavior. The LC9600 cards seem to be fine, so maybe we have to migrate everything to that. But it's that 1% difference that we consistently seem to see. So I think that's all related. And it's, like I said, it's not really an operational issue, it's just, it looks butt ugly. But it's not all bad news. So we learned a number of things during our testing. And one of them was that the SNMP polling that we did for the devices was very slow. And I noticed this as soon as we started adding more Juniper devices, the polling times went up and up. And then we found out that we can make this much more efficient by changing the way we do polling. Instead of going, I think it's column-based, we go row-based, and we introduced a number of SNMP filters. Because unlike, for example, the extreme boxes, which will typically return only physical interface data, the Junipers like to return everything they have. So that includes all virtual interfaces, and anything that they can think of is going to be there. So we would typically have over, I think, 1,000 interfaces coming back, interface points coming back by normal bulk query. And by using a proper filter, we really reduce that to only a couple hundred, like the real physical interfaces. And that helps us to reduce the polling times to really under about 20 seconds now. And that's a big improvement. And so far, that's the only advantage that I had out of all of this, that we improved at least that graph. But that's the only graph that we see and you don't. So. And I think, oh, I'm over time. Oh, I still have time. Yes.
No, actually, we still have 20 seconds left,
yeah.
Although we did go over time, because 3 minutes ago the coffee should have started.
Oh, shit.
We're not going to do questions. Like I said, we have coffee time. But if you can find Alexi, because he had a question, I see.
Oh.
If you can find him in a minute. Alexi, It will cost you a beer, because again, I saw a reward with beer. It's something with technical people and beer. And if you give them a pizza as well, they will help you a lot more. Yeah. So anyway, Thank you very much, Steven.
Good. All right.
I'll see you in a bit.